Matched Pairs, our tutorial. We've made it to week 6, and we've learned a lot of things along the way, but we're not quite done yet. In terms of material, we are now focusing on the methods required to compare two samples. With respect to R, we still have to learn how to use R scripts, which are very useful to keep our code nicely organized. Let's first get acquainted with using R scripts. We can create a new blank R script from File, New Document. Or from this icon. An R script is essentially a text document, but it's special because it allows you to execute code from within the file without having to copy and paste or retype commands every time. Shall we try an easy example first? What's 1 plus 1? On a Mac, you can execute each line by pressing Command and Enter. Or on a Windows machine, you can press F5. Or we can write more code, like 2 plus 2, highlight multiple lines, and execute them all at once, with again pressing Command and Enter. You can even insert comments by putting a hashtag in front of your comment. When this line is executed, R knows it is a comment, so it won't throw an error. You can now save this file and use it later. Our focus today will be on two sample confidence intervals and hypothesis tests for matched or paired data. You should download the R script I have uploaded along with this video to follow along. You can now open the R script from File, Open Document. You will notice that our R script has lots of commands and comments to remind us what the commands are used for. We'll begin by setting our working directory, reading in the data, and attaching it so we have access to the variable names. It's always good practice to look at the data before we begin working with it, and we can do this with the head command. It gives us a preview of the first few observations. Recall that for each skeleton, we have the Deganji error and the Suchi-Brooks error, making this a matched pair dataset. And we are interested in analyzing the difference between the two methods. Now the difference is already calculated for us, but we could do it ourselves as well, just by defining a new variable myDifference and setting it to the difference between the two methods. Notice that the subtraction is done component-wise, or line by line. If we view our difference and the one that's part of the dataset side by side, we see that they are the same. We can even double check that they are equal with the double equal sign, which is a logical question that returns true or false, again component-wise. You'll also notice that there are two NAs, which Allison mentioned in the lecture. We can even obtain the mean and standard deviation of the differences if we want to calculate anything by hand. But in this case, we must insert an optional argument na.rm is equal to true, which removes any NAs from the dataset. Now, since we are only analyzing the difference between the two methods, we have one sample yet again. It's just a sample of differences. So we can use t.test to test whether the mean difference is 0, or alternatively, whether the two methods are equal. With t.test, we also have the option of just inputting each dataset separately and specifying that they contain paired observations with the argument paired is equal to true. These two methods produce the same results. The extremely small p-value lets us reject HO and conclude that there is a difference between the two methods. R scripts are convenient when you have a lot of code to execute, when you need to execute the same commands over and over again, or when it's useful to have comments within your code. From now on, we will choose to use R scripts in our tutorials. We hope you will find them very useful.